In this video, we are going to explore and find out the wave function of a particle trapped in the infinite square well. Well, this is basically the beginning of your realm towards understanding quantum mechanics, and this is probably the most basic problem that everyone starts with. So let's dive in. So you have a particle trapped inside the infinite square well, and this has infinite height, length a, and the potential inside the well is considered to be 0. So we are interested in finding out the wave function of the particle in the box. So first of all, we begin by writing the Schrödinger equation that we know. This symbol over here is the Greek letter psi, and this represents the wave function, the total wave function of the particle in the box. And psi of x comma t can be represented as a function of space and time, and therefore we write psi of x of t being equal to psi of x times phi of t. So we're interested in finding psi x comma t. In order to do that, we need to first find out what phi of t is and find out what psi of x is. So first of all, let's begin by finding out what phi of t is. So the first step would be to plug in psi x comma t into our Schrödinger equation, and let's see where that takes us. Now notice that in our infinite square well, inside the space that we have over here, the potential inside is basically 0, right? Therefore, we could say that inside the box, this entire term goes to 0. And then we are left with the following. The next step would be to use the method of separation of variables in order to solve this second order differential equation. We divide both sides by psi of x times phi of t, and then we get now, since we are interested in finding out what phi of t is, we can assign the other term in the right side of the equation as a constant, and then we can proceed to find out what phi of t is. For reasons that will be discussed later, we will call this entire term as E. And E is basically the total energy of a particle inside the box. And therefore we write that by solving this equation, we get that phi of t has the following form. So now we have our time-dependent part. The time part of our wave function is what we got. Now we can proceed and find out what psi of x is, which means the position part. So again, we have our infinite square well with our particle inside the box. And we have 3 different regions where we are dealing with. One is region A and region C, which is outside the box, and the other one is region B. Now, notice that inside region B, your total potential is 0, and we consider that the potential outside tends to infinity. Now, in order to find psi of x, what we do is we rewrite the Schrödinger equation, but this time without the phi of t part, which is without the time-dependent part. And that follows as notice that since we are dealing with only the region inside the box, this entire term goes to 0, right? And now let's proceed with this. Now recall that when deriving the part for the time-dependent part of the wave function, we called this entire term over here as e, right? And therefore we can rewrite this as e times psi of x is equal to the rest of the thing. And with a little bit of rearrangement with the method of separation that we did, we can rewrite this as, now just for convenience, we are going to call this term the square root of 2me all over h bar as being equal to k. What this does is it allows us to rewrite our equation, our differential equation, in the following way. Now notice that this differential equation over here has the following form of solution. Now the conditions of continuity demand that psi of 0 is equal to psi of a is equal to 0. This basically means that at the edges of the boxes, you find your wave function to be equal to 0. Well, if that were the case, then we would see that c3 cosine kx wouldn't be a part of the solution, since at x is equal to 0, cosine of 0 is a non-zero value. So psi of x is basically equal to c2 times sine of kx. Now we're not done with this. We need to find what c2 is and then add the time-dependent part so that we can have the entire solution. So now our task is to find what this c2 is. Well, finding c2 is basically simple. Recall that the probability of finding your particle outside of the box, which is in region A and in region C, is basically 0, right? So all the probability revolves around finding your particle in only region B. So there's a 100% chance that you will find your particle in only region B. We can apply our probability equation, and this implies that now we know what our psi of x is, so we can compute this equation into our integral, and then we can have that. Now we have the following integral of this sort of form. Now if we solve this integral, we will be able to find what c2 is. And I will write down what the solution for this integral is over here directly without going into further detail of the integral of sine squared, and we will find that c2 is equal to the square root of 2 over a. I am not going to go through an entire solution of how this integral looks like in these bounds, but feel free to pause the video because I am attaching a snippet of what this integral looks like over these bounds. So now we have what our c2 is. So by plugging c2 into psi of x, we will get that our wave function, that position part of the wave function, looks like the following form. And we also have our time-dependent form, which looks like this. And combining this into our main part of the wave function, the total wave function, we get that psi x comma t is basically the square root of 2 all over a sine kx e to the negative I e all over h bar t. Well, that's all.